Hello. On this video, we're going to continue on sections 1.1 and 1.2 in the book. As I mentioned, I'm not covering them in the same order. I'm basically taking topics from each section and then kind of putting them together into just one lecture covering both sections. At the end of the previous video, we defined what the domain and the range of a function are. I just realized that I probably should underline the words domain and range. Basically, given a function that maps a set S to a set T, and we talked about this notation here, that's what that means. The domain is a subset of the input set, which in this case is the set S, right, consisting of the elements of S that are mapped to something. So in all of the examples that we've seen, the domain is always the whole set S. However, we'll see that that's not going to be the case in a lot of the examples that we're going to see a little bit later. And then similarly, the range of a function, again mapping the set S into the set T, is now a subset of the output set. So it's a subset of T, consisting of the elements of T which have something mapped to it. Right? And again, in the examples that we've seen, I think that in all the examples that we've seen, the range of the functions has always been the whole set T. But again, we'll see in examples in a moment that it's not always the case that the range of the function equals the whole output set T. Right? So to remember, the domain is a subset of the input set S, and the range is a subset of the output set T. And so we saw an example. We did an example about a menu, right? If you remember so I think I have the picture here. Yes, we had a menu from Taco Bell, and we had 3 items, so large drink, rice and burrito, bean, and 3 soft-shell tacos, right? And the prices for each. We created a function out of this information, right? And we saw that indeed it's a function, right? Every element of S is mapped to a unique element of T, right? And then we could also find the domain and range, right? So looking at S, every element of S is mapped to something, right? So the domain of this function F is all of S. And similarly for the range, every element of the range has something mapped to it, right? So the range of this function F is all of T. Okay, now, let's do another example in which it's not the case that the domain is all of S and the range is all of T. So suppose we have a function F here. Notice that I've written it in this notation where we just draw like the circles that represent the sets, and we draw arrows to represent what the mappings are of the elements of S to the elements of T. So if we look at this set here, or this function, first of all, notice that it satisfies at least one of the conditions of a function, right? Definitely, if an element of S is mapped to an element of T, then it's only mapped to 1, right? So for example, 1 is only mapped to B, 3 is only mapped to A, 4 is only mapped to E, and 5 is only mapped to D. Now, however, when we defined a function, so let me go to the beginning of the previous lecture. The way I defined it, I said that a function from a set S to a set T is a rule that assigns to each element, X element of S, a unique element, Y element of T. Right? Notice that this definition says to each element of S. Now, in this case, the way this function F is defined, not every element of S is assigned an element of T. For example, 2 is not assigned anything. Right? It's not mapped anywhere, and that's represented by no arrow coming out of it. Right? So that's fine. We still want to think of this as a function. Right? The idea, and this is why talking about the domain and range is useful, because that way we can still think of this as a function, but basically the function has a smaller subset that maps in the input set that it actually maps to something. That's the domain, and it actually has a smaller subset of the output set, the range, that has something mapped to it. Right, so talking about the domain and range lets us work with functions that not necessarily map everything into everything. So in this case, let's see what the domain and range are. So look at the domain. So remember the notation is capital D of F. So just look at all of the elements of S that are mapped to something, right? And basically all of them are mapped to something except 2, right? So the domain is 1, 3, 4, 5. Similarly, what's the range? Now we look at the subset of T of all elements of T that have something mapped to it. Well, A has something mapped to it, so does B, so does D, and so does E. The only element of T that has nothing mapped to it is the element C. Right? So that's not included in the range, but everything else is. So here the range of this function is the set containing A, B, D, and E. So this is the first example of a function mapping a set into a set whose domain and range are not necessarily equal to the input and output sets. Now we're going to see this happen a lot because in the next topic that we're going to cover, just right now, we're going to be looking at functions that mostly, basically all of them, for all of the examples that we're going to see from now on, are going to be functions mapping the set of real numbers into the set of real numbers. However, we're going to see that for a lot of these functions, the domain is not the set of real numbers, it's smaller, and the range is not the set of real numbers either. It's the smaller set. So we'll see that in a moment. So right now we're going to talk about representing functions using algebraic expressions. Right? So again, this is something that you probably saw in algebra. You should have seen in algebra in high school. We'll refresh things a little bit here. Right? So example 7. Suppose that we have a function that maps the set of real numbers into the set of real numbers. Remember that this is the symbol that we use for the real numbers. Kind of looks like an R with an extra leg. So you can draw it something like this. So we have a function mapping the real numbers into the real numbers given by f of x equals x plus 1. Okay. Now, let me say a couple things. A lot of times, it is useful to graph a function to better understand its behavior. Right? So what's a graph of a function? It's basically a visual depiction of what the function looks like. Now, what this graph is depicting is actually all of the ordered pairs in the function. Remember that we can represent the function as a set of ordered pairs. Where the first coordinate are the inputs, and the second coordinates are the corresponding outputs. So a graph allows us to visually see what is going on, right, with these ordered pairs. So let me make a couple notes here before we actually start graphing. First, since a graph is used to visualize the function as a set of ordered pairs, it's useful for us to first write out what that set looks like. Okay? So now, here, the domain and range of f are infinite sets. Right? The set of real numbers is infinite; it has infinitely many elements, and so does the output set R, because they're both the real numbers. Okay? So that's a problem because we can't enumerate infinitely many ordered pairs. In fact, the set of real numbers, in terms of how infinite it is, it's a larger infinite than the set of, for example, rational numbers, or the set of positive integers, or the set of integers. Right? So really, there's no way for us to write down every ordered pair. Right? So what we're going to do is just write it in a general form, right? But that still is going to give us a little bit of information on how to graph this function. So by definition, f is the set of all. Okay? So we know we're looking for ordered pairs. So ordered pairs of the form x comma y, okay, such that, okay, well, x has to come from the real numbers. Right? So x is an element of the reals. And what is y? Remember that y is the image of x under this function. Right? We're given that an element x is mapped to the element x plus 1. Right? Remember, that's what f of x means. F of x is the image under f of x. Right? What that means for us is that y here has to be equal to x plus 1. And this is how you can write this function as a set of ordered pairs. A set of all x, y, such that x is a real number, and y equals x plus 1. Now, I put a picture of a graph here, and actually let me move it up a little bit, if I can. All right, so what we're going to do here is we're going to plot some of these ordered pairs. Now, of course, we can't plot all of them because, again, there's too many of them. There's infinitely many. But we'll plot a couple, and then from that, we should just get a pretty good idea of how the function looks like. And basically, we're just going to fill in the gaps. Okay? So how do you graph ordered pairs? Okay. So basically, you create a, so here I put in a picture. But basically what you do, so let me do it up here. If you want to do this in your notes, for example, you create two lines that are perpendicular. So a line like this and a line like this. Now, the line that's, the line that's horizontal, we usually are always going to denote by x, and this is going to denote the input values. Remember that x denotes the inputs. And then the vertical line, we're going to denote by y, right? Or remember, this is just another way to say the output. The outputs. And then how do you graph ordered pairs? Well, basically, if you're doing this by hand, you can create a couple dashes. And usually these dashes are just jumps of distance 1. So the first, here we have 0, then x equals 1, x equals 2, etc. Same for the vertical axis. We start with y equals 0, y equals 1, y equals 2, etc. So if you can see, I'm kind of just replicating the graph that I already put in. And then how do you graph ordered pairs? Well, let's first pick one ordered pair. Let's say we want to find the ordered pair that has x coordinate x equals 0. So the x coordinate is 0. What's the y coordinate going to be? Well, by definition, y is equal to x plus 1. Here we're saying that x equals 0, so y equals 0 plus 1, which is just equal to 1. Right, so this is one ordered pair in this set that constitutes this function. How do you graph this, or how do you plot this? It's very easy. I'm going to do it in both pictures. I'm just going to do it once in the picture on the right, and then I'm going to move to the picture on the left. But basically what you do is, x tells you the position in the x-axis. Right? So we're working with x equals 0. So we want to stay here where x equals 0. And then y equals 1 is telling you to move 1 unit up in the direction of the y-axis. Right? So x equals 0, y equals 1 is right here. So this is the ordered pair, x equals 0, y equals 1. Say we want to plot another ordered pair. Say we want to find the ordered pair that contains as x coordinate x equals 2. So if x equals 2, by the definition of the function, the y coordinate is x plus 1, so this is equal to 3. And again, if you want to plot this, x equals 2 is telling you, let me draw some arrows actually, move 2 units to the right, x, and then y equals 3 is telling you to move 3 units up. So 1, 2, 3, and then here is the point 2, 3. Now, if x is negative, then that's telling you to move instead of towards the right, towards the left. And then if y is negative, it's telling you to move down instead of up. So let's do just one example of that. So let's do the coordinate with the ordered pair with x coordinate equal to negative 3. Now the y coordinate is going to be x plus 1. If x is negative 3 plus 1 is negative 2. Okay. So how do you plot this? This is telling you, starting from the point 0, 0, right, we go negative 3 units, right? So that means 3 units towards the left of 0. Right? So 1, 2, 3. And then y equals negative 2 is telling you to go 2 units down in the y direction. So 1, then 2. And this is the point negative 3, 2. So plotting points is very easy. Basically, x starting from the point 0, 0, and the point 0, 0 is sometimes called the origin, and that's always where the x-axis crosses the y-axis, right? Or where the x line crosses the y line. So starting from the origin, if the x values are positive, move in the right direction. If they're negative, move in the left direction. If the y values are positive, move up. If the y values are negative, move down. It's as simple as that. Now, just so that the picture looks a little bit better, let's plot it in this actual xy plane that I just copied in. So we have the point 0, 1. We have the point 2, 3. Then we have the point negative 3, negative 2. Now, we could keep plotting more and more points, but you're going to see that basically this is the graph of something that looks like a line, right? A straight line going through all of these points. So once you've graphed or plotted enough points so you have a general idea of what the graph looks like, then you can simply just fill out the rest. So I know this is going to be a line. So it's going to look, something like that. It should be straight. I'm sorry that it's not straight. I'm not too good, but that's basically how the graph looks like. Of course, here I'm only graphing on the for x values between negative 9 and 9, and y values between negative 9 and 9. But it's understood that x can go out infinitely and y can go out infinitely. Just we're not going to plot the whole graph because it's infinitely large. Okay. So this is how the graph of this function looks like. It's just a line going through these points. Okay. Now that's basically how you graph. This is an easy example, so we'll try a couple more. So let's go to another page. Let's do example 7. In this case, we're going to do something very similar. What we want to do is graph. So let me write here. Graph the function f, and again, this is going to be mapping R to R, given by f of x equals the square root of x. Now, before I do this, notice that in example 6, right, if we look at what the domain and the range are, right, and we'll talk more about this later, how to find the domain and range for functions like this. But basically, if you're asking what the domain is, you're kind of asking what inputs am I allowed to put into my function. Right? So your function in this case is given by f of x equals x plus 1. Right? What x values can I plug in? Well, there's nothing you can't plug in. And we'll see with this example, right, so example 7, an example of where you can't plug in some values. But in this case, we can plug in anything. And so the domain here would be the set of all real numbers. Now, the range is a little bit easier to calculate, right? Because for the range, we're asking what values of R, of the set of real numbers, have something mapped to it by this function. So maybe from the picture, it's completely obvious that the range is also the set of all real numbers. Why? Because it doesn't matter what y value you choose, this line here is eventually going to reach that y value, right? Whether it's a very large y value or a very large negative y value. So again, in this case, the domain of this function would be the set of all real numbers. Oh, sorry, the range. Now, I know I'm not saying too much about this. It's on purpose because we're going to talk more about this in a moment or a little bit later. But for now, you can kind of try to understand why it's the case that the domain and range of this function are, in both cases, a set of real numbers. Now, for example 7, graph the function f, mapping the reals into the reals given by f of x equals the square root of x. Now, as before, I'm first going to write it in set notation, right, as ordered pairs. And so by definition, this is the function given by the set of all ordered pairs, where the first coordinate is x, the second coordinate is, actually, let me write it the same way, y, oops, such that, again, since this function is mapping the real numbers into the real numbers, then we have that x is a real number, and y is equal to, what is it, square root of x. Now, however, you have to be careful here. The reason is that even though the domain or the input set in this case is a set of real numbers, it's not necessarily the case that the domain is all of the real numbers. So I have to be careful here, because when I say that x is an element of the reals, right, I'm saying that x can be anything. But we'll see in this case that, and maybe you already know, if you remember from algebra, that x can't actually be everything. Right? So let me just say that this we have to fix. This is not entirely true. Right? Because it's not the case that x can be any real number. Right? But let's go ahead and try to plot a couple points. Right? So we have square root of x, so let's plot some simple ones. Right? So if I plug in, or if I want to find the coordinate, the ordered pair with x equals 0, what's the square root of 0? This you can just memorize as a definition, that the square root of 0 is always equal to 0. So in this case, we have the point 0, 0 in the graph. Similarly, let's say I want to find the ordered pair with coordinate x equals 1. Then I have to find the square root of 1 for the y coordinate. But again, the square root of 1 is just equal to 1. Now, say I want to do the ordered pair with x equals 4. Now, I need to find the square root of 4. If you remember how the square root works, the square root of 4 is equal to 2. Right, so I have the point 1, 1. Then I have the point 4, 2. Now, how am I getting these values for y? How do you take the square root of a number? Well, basically, the square root function, so the square root of a number x, actually, let me use a different variable. So the square root of a number a is a number, let's call it b, such that and we only work with positive, so let me say is a positive number, or non-negative, so positive or 0, such that this positive number or 0, let's call that number b, such that b squared equals a. Right? So whenever I ask you to find the square root of 4, for example, you're basically just looking for a positive number such that if you multiply that number by itself, you get 4. Right? So, for example, this is how I got the square root of 4 is equal to 2. And again, some of you might already know this, but I'm just reminding you how it works. Right? So, square root of 4, and again, we only choose positive numbers or 0. So square root of 4 is equal to 2 because 2 squared equals 4. Right, etc. Now, also because of this, we can't actually write or include in our domain values of x that are negative. Why? Suppose that we are trying to find the square root. Okay. Suppose that we're trying to find, and I'm going to do a specific case, but it works for any negative number. Suppose that we want to find the square root of negative 1. By definition, the square root of negative 1 is a number b, positive number, or 0. So I forget it's right. That is a positive number or 0, such that b squared equals negative 1. Now, if you remember from arithmetic, if you multiply a number by itself, it's always going to be positive, right? So, for example, negative 2 times negative 2 is equal to positive 4. 2 times 2 is equal to 4. Negative 7 times negative 7 is equal to positive 49. So it's impossible for us, in the set of real numbers, to find the square root of a negative number. That means that x is not in the domain. And this is where I mentioned in the previous slide that to find the domain of a function, and again, we'll talk more about this later. Usually what you do is that you look for the values of x that you can plug in. And this is the domain into the function. So in this case, we can plug in any number that's positive or 0, and we're going to get a function value out of it, right? Because we can take the square root of any non-negative number. Non-negative meaning 0 or positive. However, once we have negative numbers, then we can't do that. Okay? So any negative number is not in the domain of this function. And so if I want to graph this, let me do one. Oh, this is fine. If I were to graph this, I would just connect these, and it would look something like this. There's nothing to the left of x equals 0, right? Because the function is not defined there. So I only draw the graph for x values greater than or equal to 0. And this is how the square root function looks like. So now I can fix this here, right? So I know that these are ordered pairs. X can't be any number, any real number. X has to be greater than 0, greater than or equal to 0. So just fixing that there. And then as we said, in this case, the domain of this function is, now there's infinitely many numbers here. Okay, so I don't want to write all of them, but I can just write it's a set of all x that are real numbers such that x is greater than or equal to 0. Right? That's what we saw. We can plug in any number as long as it's 0 or greater. Again, if that's a little bit confusing, don't worry too much about that. We'll talk more about it later. For now, just understand how to graph functions. So just plot a couple ordered pairs, and then use your intuition to see, okay, I plotted enough that I know how this graph is going to look, and then just connect the dots, basically.